This is the scariest sight that anyone in traffic wants to avoid. Sinkholes and shattered road surfaces. This is not just a matter of safety. It is also a fierce economic battle, because maintaining sustainable roads is a problem worth tens of billions of dollars worldwide. To see the scale of this battle, look at the United States. Even a leading superpower must spend $30 to $50 billion every year just to repair and maintain the federal highway system from severe deterioration. This massive figure shows just how difficult it is to keep a road existing against the power of nature. But in the harshest lands of southern India, where states like Kerala or Tamil Nadu face monsoon seasons that cause soil erosion and hot summers that deform asphalt, genius engineers here have found a way to win this billion-dollar problem using a material no one expected: coconut waste. They turn this waste into geotextiles, a type of super material that helps stabilize the soil and provides incredible durability against erosion. But what is the purpose of turning coconut fiber into fabric? The answer is to create solid roads capable of carrying thousands of tons even on the most unstable ground. So what process has turned rough coconut husks into heavy weapons that even American engineers admire? Let's decode this technical secret with us right now. Don't forget to like and subscribe to the channel to support our analysis of megastructures. Let's get started. To solve the infrastructure problem, Indian engineers did not look into chemistry labs, but instead looked at the biological structure of the coconut. India is currently the world's coconut capital, with a massive output of over 19 billion coconuts per year, concentrated mainly in the southern states. The source of coconut husk waste here is nearly endless. But what truly amazed the engineers is the inert ability of coconut fiber against environmental impacts. The secret lies in lignin, a natural polymer that makes up an extremely high percentage of coconut fiber, acting like a protective resin coating the cellulose fibers. This lignin content helps coconut fiber have natural antioxidant properties and prevents attacks from bacteria or mold, even when buried in moist soil for decades. Besides, coconut fiber also possesses superior tensile strength, allowing it to withstand the expansion and shifting pressure of soil and rock layers without breaking. However, to fully exploit this power, the pre-processing must be extremely strict. Workers must harvest coconuts that have reached standard ripeness, then perform manual dehusking to keep the fiber structure intact. The husks are then dried in the sun continuously for 2 to 4 weeks to perform an important physical transformation process. The moisture inside the coconut husk will be reduced from 65% to exactly about 15%. Controlling this moisture not only helps the fiber reach its highest flexibility, but also prevents the natural fermentation process, keeping the material stable before production. This is the key to turning agricultural waste into a type of geotextile with a lifespan equivalent to expensive man-made materials. Once the coconut husks reach the ideal moisture, they are moved to the most important stage of the process: decortication. Here, specialized decorticating machines use high-speed rotating blade systems to break the hard outer shell. This process completely releases the flexible coconut fibers while removing dust and unnecessary debris. However, the newly separated fiber is not yet up to standard for highway construction. They need to be dried for an additional 3 to 7 days to stabilize the structure. Then the engineers perform a clever technical step: twisting the coconut fibers into large bundles. This twisting process not only increases the material density, but also ensures maximum tensile strength, preventing the fibers from breaking when going through high-capacity industrial weaving machines. Next is the weaving process, where the raw bundles are fed into the weaving machines to form tightly interlaced networks. This is when coconut fiber geotextiles are born. Look at the impressive production efficiency of Indian engineers. With just 100 kilograms of coconut fiber, they can create 250 to 300 meters of finished fabric. And what amazes Western countries most is the economic factor. The production cost per meter of fabric only ranges from 1.20 USD to 1.80 USD. This price is only a fraction of the cost of synthetic geotextiles made from petroleum. Yet it provides a solution that is many times more sustainable and environmentally friendly. These brown mesh sheets are now ready to become the solid skeleton, protecting the soil foundation for infrastructure megaprojects. Once the geotextiles are ready, the construction site begins operating under a strict technical sequence to ensure the road can last for decades. The process begins with a fleet of bulldozers and specialized motor graders to strip away the entire layer of vegetation and topsoil on the surface. Completely removing organic impurities is mandatory to prevent sinking caused by biological decomposition in the ground later on. After leveling, heavy vibratory rollers weighing 15 to 20 tons enter the site. These machines use strong vibrations to rearrange soil particles, achieving a compaction density of 95% to 100% according to the Proctor standard. For acceptance, engineers will perform a test roll. They have a heavy truck drive over the surface. The standard ground must be so hard that it is not allowed to leave even the slightest indentation. Once the ground has reached absolute compaction, the biological armor layer begins to be installed. Massive rolls of coconut mesh, usually 2 to 4 meters wide, are rolled out along the leveled road. To ensure continuity, the sheets are overlapped at the edges by 15 to 30 centimeters. Workers must stretch the corners of the mesh to completely eliminate wrinkles, as any air pockets could cause sinking or cracking later. Immediately after, thousands of U-shaped steel anchors, 15 to 20 centimeters long, are driven through the mesh into the ground. The anchor density is distributed in a 1 meter square grid and reinforced more densely at the overlapping positions to keep the mesh tight. Next, dump trucks proceed to pour small gravel or uniform stone dust onto the fabric surface. The motor grader continues to work to spread this cushion layer evenly with a design thickness of 10 to 15 centimeters. Immediately after, a light steel drum roller will pass over to press the small gravel into the openings of the coconut mesh. This process creates a mechanical interlock, helping to protect the coconut fibers from being torn by the sharp edges of the base course stones above. This is the main load-bearing layer of the road, using a graded aggregate mixture of various sizes, from fine stone dust to large crushed stones with sharp edges. The stone is spread in layers, and each layer is compacted with heavy vibratory rollers. During compaction, the small particles will fill the gaps between the larger stones, forming a tightly bonded mass. The coconut fiber layer underneath now acts as a load-bearing frame, preventing the base course from sinking into the soft subgrade while maintaining drainage for the entire structure. The final transformation begins as hot asphalt maintained between 135 and 160 degrees Celsius enters the specialized paver. Using advanced laser sensors, the machine distributes the material with pinpoint accuracy across the road surface. Immediately after, a fleet of rollers works in coordination to compact the multiple layers, eliminating all air gaps and sealing the surface. The result is a smooth, perfectly flat highway built to withstand heavy loads for decades, according to international standards. We have now walked through every stage of constructing a road reinforced with coconut fiber. The success of this project proves an essential principle in modern engineering. The most effective solution is not always the most expensive. By combining natural materials with precise engineering, these roads remain durable against extreme moisture and heat, forces that cost billions of dollars in maintenance worldwide. The coconut husk, once considered agricultural waste, has become the solid backbone of modern highways. This is a testament to human creativity when facing environmental and economic challenges. If you enjoyed this analytical deep dive into mega projects, please support us by hitting like and subscribing to the channel. Thank you for joining us today, and we will see you in the next episode.